Hello guys, today we are going to solve some problems in the Matlab for the Z transform. Okay, week 5 M script X. Okay, as always we do, we need to give the clear all, close all and CLC commands in here, just like this one. Okay, so in the week 5 we talk about the inverse Z transform or the Z transform of the any variable. Okay, we will start with these things just like this one. Okay, firstly we need to define the fk parameters in here just like this one. This is a symbolic toolbox variable which is given in here with the parameters of the k. We can do that because the Matlab enable us to define any symbolic function based on the based on the variable. Okay, and also we need to give the a and t sampling period and w, which is the angular frequency of the R system. Okay, firstly just remember that we can define the fk as equal 1, the unit step signal in here just like this one. And so in order to take the Z transform of these terms, so we can use the pretty simplified. This is good looking for the for the transformation results. Okay, simplify the equation in terms of the Z value in here, and the pretty is the pretty. Okay, this returns to the pretty looking for the for our equation. In order to take the Z transform, we can use the Z trans function in here, just like this one. And so we can fit the F in here, just like this one. And then if we run this code, and then we will have the Z divided by Z minus 1. Okay, this is this is the unit step signal transformation of the Z transform. Okay, we can use this function in order to get the complex formulation of our algorithms or the R questions. Okay, we don't need to use the write and solve everything by hand. We can use the Matlab program. Okay, and so another function which is given in the t times k, which is the ramp signal with based on the sampling period of the t. Okay, and so we can use the pretty simplify in here just like this one. The Z trans F can be written as in here. Okay, and so we can comment these things, and then we will have t times Z divided by Z minus 1 square in here. Okay, just remember that we have the second order equation in here, just like this. It's the square form, which means that we have the signal in the increased form at these notations. Okay, and also we can utilize the exponential function minus a times t times k. This is the general solution of the exponential term in time domain. And also we can write the pretty simplify function Z trans F in here. And so if we have this notation, and then we will have the exponential form of the Z transform. Okay. So we can apply this value on the sinus signal. Okay, just like this one, the angular frequency, sampling period, and the k, the index of the R basis. Okay, and so the pretty simplify Z trans can be called using these terms, and then we will have the Z transform of the sinus signal. Okay, or can use the fk exponential a minus a times t times k times sinus w times k times t. Okay, we can use it, and also we can copy of these things in terms of the we can get the Z transform of these terms, or we can use the t times k plus 1 times cosinus, for example, wkt times sinus w kt. We can use it, this transformation, and so this will return to the what our results in terms of the what the z transformation domain. Okay, so this easy to manipulate this value using the what this notation. And so if you have any question or any solution in the continuous time domain, we can easily convert these values into the what, into the z transform using these informations. Okay, just remember that. So the other example is directly related to the what, the transfer function definition in the z transformation domain. Okay, so in the first place we can define the num to 0, and then can be defined with what the 1 minus 0.5 and 0 25. Okay, and so in order to define the system in here, just like this one, system tf num, then this will return to the what, to our continuous time domain signal. Okay, 2s divided by s squared minus 0.5s plus 0.25. But in order to create the z transform or the discrete domain in here, we need to apply the what, the ts sampling period in here, just like this one, 0.1. Okay, and also we need to feed into the what, the tf function in here, just like this one. And so we have the 0.1 second sample time for a given function in here, just like this one. Okay, we will set these values in here, and also we can visualize our results in terms of what the step c's value in here. Okay, so we have the r signal in here with the values of the what, these terms. Okay, and so this is the step response, unit step response for a given discrete time signal, which is defined with the what, with the num and them values of these terms. Okay, these are the results, and so we can easily analyze this signal based on this information, or we can define to another function with the based on the what, the different sampling period, because the sampling period is the most important thing in the discrete time domain, because if we have any continuous time signal, we can use the different values of the sampling rate. Okay, and so if we can use the different sampling rate, and then we can define the different function or different response based on this sampling ratio. Okay, just this one, c's tf num then and ts can be given in here, just like this one, and so hold on can be given for what, for drawing the same figure with the new values of these terms, and also we can apply the step response in here, just like this one. Okay, so we have two kind of system response in here. First of all, we have this red line in here, the other is blue line. Blue line is the 0.1 second sampling period, the other one 0.01, 10 milliseconds. And so see that if we have the same system in the continuous time domain, if we apply the different sampling ratio, and then we will have the different output results at this nomination. Just remember that this is important, because if we select the correct values of the sampling rate in here, and then our system response is affected based on this selection. Okay, so these are the questions about the first example. And second, we can create the our system based on the zeros and poles. For example, if we want to use the 0.1 and minus 0.1 poles, and we can assign the gain value in here, just like this one. And so how can we generate this function in here? Poles figure TS can be assigned, for example, 0.1, 100 milliseconds, and Cs can be defined with the zero pole gain function in terms of the zeros, poles, and gain and TS. Okay, and so if we run this code, and then we will have the 1 zeros and 2 poles at this nomination in terms of what the sampling time with the what 0.1 seconds. Okay, we can use it in this format also. Okay, and so we can create a step response in here just like this one, the step C's. Okay, and so if we run this code, and then we will have the R response in terms of what these nominations. Okay, and so at the steady state we have the 0.85 number for the amplitude values. Okay, and so hold on can be given in here. TS 0.2 can also be assigned in here. This is a different sampling rate. Okay, and so the C's can be copied by using these terms just like this one. Okay, the Z transform function is the same, but the TS value is different in here. Okay, and also we can write what the step C's value, and also we can write the hold on in here. Okay, and also we can utilize the 0.3. This is the sampling rate of what our algorithm or the microcontroller structure. Okay, and so we can give the legend value in here just like this one, the legend 0.1, 0.2, and 0.3. Okay, and also we can open the grid in here. So we have 3 different response in here just like this one, 0.1, 0.2, and 0.3. The yellow line is the lowest values for the what the frequency, but the 0.1 is the highest sampling rate in here just like this one. Just see that the R algorithm or the R response is same with the what the 0.2 and 0.3, but we have one condition with a different based on these signals. Just see that if we use the slowest sampling rate, sampling period in here just like this one, it's indicating in the blue line, and so we will have the what the lowest transient function in here. But if we have using the highest sampling period in here, the shape is what is same with the previous one, but we can extend our results in here. In the real-time application, it's the important parameter to what to control your signal, or to apply the filter, or to apply the discrete domain signal analysis on your measurements. Okay, just remember that. So this is the second example about our response. And 3, we can write the zeros value in here, 0, 0, poles, for example, minus 0.1, minus 0.1, and gain can be assigned with the 1. Okay, and so we can draw the figure in here just like this one, and we can set the different values in here. Okay, but just remember that in the figure we can copy up the whole of these things in here just like this one. It's the same in here, but with one basic difference, which is the we can set the impulse response in here just like this one. Okay, what's the impulse? Impulse is the application of what the direct delta function on the continuous time signal, or in the discrete domain we have the one value at the 0 in this, and we can apply the whole the system based on the what this nomination. And so if we rerun this code, and then we will have the different kind of the what the impulse response in here based on the what the different values of the what the R sampling rate. Okay, this is most important, because if we have this signal, and then we can convolve the whole the signal based on the what based on the R system, Z transformation system. And so this generates to what the R template pattern for the R Z domain transfer function or the R systems. Okay, and so if we have this condition, and then we can convert everything in the time domain, especially for the discrete time, and then we can generate the different responses for the for a given different sampling period in our signal. Okay. So in the third part we can have the our continuous system. For example, we can assign the b is equals to 5 and a is equals to 5. Okay, and we can assign the num values with the b, and denominator can be assigned with the 1 and a. And so this continuous transfer function can be defined with the num and then. Okay, just like this one. So if we run this code, we have the transfer function with the values of the 5 divided by s plus 5. Okay, so we can draw the figure for a given the system continuous function with the unit step response in here, just like this one. This is the step response of our continuous time signal. But what about the definition of if we convert this continuous function based on the discrete time domain for a given sampling period? How can we obtain the output response in here? For the discrete operation, we must say that the ts is 0.1 in here, just like this one. The num can be assigned with the b times ts, because the R conversion is based on the forward difference equation. Okay, and so this gives us the b times ts in here. And also we can give the denominator in here just like this one, 1 comma minus 1 minus ts times a. Okay, these are the three discrete time transfer function for a given the 5 divided by s plus 5. Okay, and so this disk 0 1 can be given with the tf, num, then and ts. Okay, these are the z transfer function based on the 0.1 second sampling period. Okay, this is a discrete transfer function. And so how can we compare the R continuous results with the discrete one in here? Firstly, we must say that we should give the hold on in here just like this one, and step can be applied to the disk is 0 1. Okay, and so if we have this signal and then we have this kind of output in our system, it's converging to the our steady state response. But just remember that we have this signal information, and then our microcontroller or the embedded system sees this signal just like this one, not this one. This is the continuous one. But if we are taking any measurement from the system, such as using the ADC converter, and then we will have this kind of signal inputs in here. Just remember that. Okay, and so x lim 0 to 2 and y lim should also be given in here 1.2. Okay, these are the comparison for the for the discrete and the continuous time output. This is most important because in the real life we have the continuous signal, but in your microcontroller structure or the discrete time system, we just observe these red lines in here, just like this one, for a given the sampling period. Okay, and so we can also increase the sampling period in here, just like this one. 0.1 and 0.2. Okay, and also we can use the hold on function in here, just like this one, 0.1, and so we can write the legend in here, the continuous one, and discrete 0.1 sampling period and discrete 0.01 period. Okay, and so if we rerun this code, and then we will see that if we have the 0.1 seconds in here, and so there could be any mismatch between the what the continuous to the what the discrete one. But just see that if we sampling the signal based on this information, and then the R error between the continuous to discrete is diminishing, right? Because if we take any data in here at the sampling period of the 10 milliseconds, and then we can converge the continuous results. But maybe this is not possible, because in your microcontroller structure there could be many codes to be implemented in your system. For example, if you have any microcontroller code, for example the STM code, and then maybe you cannot run or cycle your system at the rate of the 10 milliseconds. This is an error case for the mismatch between the real and the discrete time signals in here. And so you need to optimize your system in order to select the proper values of the sampling period, even if you are designing the controller or the filter design, which is the same in the math. Okay, so this is the X3 in here, and X4 Matlab, and Z-plane can also be defined in here. What's a Z-plane? Z-plane is utilized to check the stability of our discrete time system, because stability is the most important thing in the discrete time domain. If we don't have any stable system, and then we cannot control or filter any signal. Okay, and so firstly we need to define the num values in here, just like this one, 1 and 0.5, and then is the 1 minus 1 and 0.25. Okay, and so this is the system of the Z, right? TF and num, and TS can be defined also in here. TS 0.1, for example. If you run this code, and then we have this output. These are the Z transformation or the pulse transfer function for a given system. Okay, and so how can we check the stability of this system in here? Firstly, we don't need to use that, because if we have the denominator in here, just like this one, we can find the poles of our system by using the roots, and then okay, these are the poles for a given system, 0.5 and 0.5. And so if we have this condition, and then so a stable condition can be created in here with all values of the absolute values of the poles is smaller than 1. And so if this is the true for all the poles, and then we can say that this system is stable. Okay, and so this poles in here, just like this one, and this we can write this nomination in here is the system stable, and num to str can be used in here is stable function. Okay, and so we can see the R results in here. Okay, and so we have the roots. Okay, and so this is the system is stable is the 1. For example, if I choose this value is the 50, and so our system is also stable. But if we are using the 10 in here, just like this one, and so the logical returns the 0 or the false value, because we have the what the root value at the 9, which means that it's bigger than 1, and so logically it's not stable in here. Okay. And so how can we check the another terms in here, just like this one? We can assign the TS is a 0.01, and sys disk can be defined with what the TF values in here, num, dan, and TS. Okay, and so we can apply the step response in here, sys disk at this time, and so if we run this code, the system just see that is stable. But if I choose the -10 in here, just like this one, and so we have our signal goes to infinity values, just like this one, 12 times 10 over 58. Okay, so this is how we can check the discrete time stability formulation based on based on these conditions. Okay, that's all for the 5 Matlab examples. Just remember that we can utilize the whole things in order to check or to test our algorithms or the system or the proofs related to the discrete time signal notation. Okay.